Hi, I'm Rob Lewis. The work I'm presenting is joint work with Johan Commelin. To give a quick overview of our project, we've formalized in Lean some of the theory behind Witt vectors. Witt vectors are a mathematical gadget that's used in modern algebraic number theory. Specifically, we've constructed in Lean the type of p-typical Witt vectors. We've defined its ring structure, and we've proved that the ring of Witt vectors over the finite ring Z mod p is isomorphic to the p-adic integers. This talk is too short to go into any real detail. So my plan is to explain why this is an achievement and to show a particular proof technique that we used. And then my co-author Johan will go into more detail in the longer talk. So why is this an achievement? Witt vectors are a notoriously difficult mathematical thing to master. There are a lot of details that are folded into the construction at the very beginning. And then later on, when you're trying to prove things about them, it's completely intractable to actually look at these details. Essentially, you have to enforce an abstraction barrier. You have to follow higher level strategies for your proofs. And the justifications for why these higher level strategies actually work, well, they really take some mathematical maturity to understand. So this sounds very hard to formalize. Proof assistants don't have a sense of mathematical smell. They don't know when you're doing something wrong. So we need some new techniques. What we've done is isolate the key mathematical insights that really justify the strategies for computing with Witt vectors, which are really not spelled out in the literature. And we've wrapped these insights in little bits of metacode that allow us to simulate the informal reasoning patterns in Lean. As was put by one mathematician who's familiar with the frustrating details of dealing with Witt vectors, we've tamed the beast, so to speak. So the underlying data of a Witt vector is actually very simple. We're going to fix a ring R and a prime number P that we'll use in a second. A p-typical Witt vector is just an infinite sequence of elements of R. Traditionally, we write it from right to left. The complexity of this definition comes when we define the ring operations on this type. They're not component-wise. And we're going to look at addition as an example. The nth component of the sum of x and y is a polynomial function, let's look at S2, applied to the 0 through nth components of x and the 0 through nth components of y. And these polynomials, S2, S1, et cetera, these depend on the prime number p. So in a 10-minute talk, I'm not going to go into more detail here. Suffice it to say that the details of this construction are pretty intricate. We want to avoid thinking about this as much as possible. So we're all familiar with formalizations. When you define a new kind of object, you need to say what you can do with that object, and you need to prove a bunch of lemmas about how the different operations interact. So there are a bunch of functions that go into the basic Witt vector API. Again, I'm not going to go into detail about any of these. I just want to point out the ghost map W at the bottom here, which maps a Witt vector into an R sequence, a sequence from the natural numbers to R, which is also a ring that has the more familiar component-wise ring structure. In general, this map is not injective. And this is going to appear when we talk about our strategies. The challenge is, how do we prove properties of these operations without actually looking too hard at the definition of the ring structure? And there are two strategies that appear in the literature that we've kind of synthesized here. The first strategy builds some scaffolding. You step up through levels of complexity of the ring R that you're working over. This works, but it's tedious. Strategy 2 is faster, it's freewheeling, but it sounds, at least as we've presented it here, it sounds unsound. Why should this actually work? Well, so here's some mathematical maturity comes up again. If you're trained in this area, these two strategies are basically the same thing. You can justify strategy 2 by noticing that it's a reformulation of strategy 1, and strategy 1 obviously works, so you're good. But the details of actually carrying out these strategies are very different. And if you can't recognize the similarity here, you're stuck with the slow fumbly one. We'd like to use the second one as much as possible, but it sounds really hard to formalize. And in fact, in Hazelwinkel's presentation of Witt vectors, he warns of pitfalls when you're using this strategy. If you don't restrict yourself to something called uniform calculation, or universal calculations rather, you're going to run into trouble. So you'd better know when you are dealing with only universal calculations. So our insight is that by universal calculations, essentially what we mean are calculations that are done on polynomial functions. The notation I use here is a little more explicit than we'd see in informal literature. Normally, the dependency of this function f on R wouldn't be noted. We just talk about f. But this really obscures what's going on. So we say that a function f is polynomial if there's a family of polynomials phi, such that for every ring, if we look at fr, and if we look at the nth component of fr, this is given by the nth polynomial phi applied to the coefficients of the input x. The quantifier order here is important. Phi does not depend on the ring R. And this definition is key because of its extensionality rule. If we want to show that two polynomial functions are equal, then it suffices to, first of all, work over the integers instead of our original ring R. And then we can just apply the ghost map to both sides. And remember that the ghost map moves us into the familiar ring structure R to the n. So these calculations are really much more tractable. You should also note that morally, we can think of some generic ring in place of the integers. If we prove this for some ring that we know nothing about, then we can obviously specialize that to the case of the integers. Okay, so with this definition, this theorem in mind, we can reformulate our strategy 2, show that both sides of our identity are polynomial functions, and then use extensionality to reduce this to a computation on ghost components. So this is great. Not only are ghost component calculations easy for us to do, they're in a convenient ring, but showing that things are polynomial is actually pretty simple too. Essentially, we're going to have to prove one lemma after defining each of our API functions that says this thing alone is polynomial, and then compositions are all handled completely automatically. So with some fairly simple metaprogramming that we describe in our paper, we can actually make this strategy look exactly like it would look on paper. So this example is one of many similar identity proofs that show up in our formalization. And we simulate the strategy of ignore that the ghost map isn't injective, apply it anyway. We're going to step through the tactic state in these first two stages. So notice that here, we're working over some ring R. After I apply the tactic ghost calc, we see that we've taken the ghost component of each side. If we're able to prove the original goal, if we can prove for each n that the nth ghost component applied to the left-hand side is equal to the nth ghost component applied to the right-hand side. Under the hood, if you look at that extensionality theorem, it's actually the case that this ring R has changed. This is not the same ring R that it was before. But the only hint that it's changed is that the name of this instance, its commutative ring instance, has changed. Otherwise, it looks exactly the same. And then after this point, we can do a simple induction and then simplify. This goal over computing with ghost components is provable by standard rewriting. And this pattern shows up again and again. For all of these identity proofs, we apply the ghost map, we do minimal or no preprocessing, and then we call the simplifier. So this works in practice. We built enough of the Witt vector API, proved enough of these relations to prove a fundamental theorem about them. This is not the focus of the talk, so I'm going to leave the details here again for Johan. The main takeaway message for this short talk, to me, is that with the right idioms, we can formalize mathematically mature topics. And furthermore, that trying to formalize these things can bring these right idioms to the surface. They're obscured in informal presentations, but formalizing makes us really think about them. Our project is not huge, and some pretty elementary metaprogramming helps a ton, not only to keep things short, but also to keep things what we consider very mathematically legible. So thank you very much for your time.